Hello friends, in this video I am going to discuss about first law of thermodynamics applied to open system and derivation of steady flow energy equation. For any system and in any process, the first law of thermodynamics is given by Q equal to delta E plus W, where E is all forms of energy that is stored in the system. For pure substance, that E is equal to Ek plus Ep plus U, where Ek is kinetic energy, Ep is potential energy, and U, the residual energy stored in the molecular structure of the substance. Then Q equal to delta Ek plus delta Ep plus delta U plus W. When there is mass transfer across the system boundary, the system is called as an open system. Most of the engineering devices are open system involving the flow of fluids through them. Equation Q equal to delta Ek plus delta Ep plus delta U plus W refers to the system having particular mass of substance and is free to move from place to place. Let us consider a steam turbine in which steam enters at high pressure, does work upon the turbine rotor, and then leaves the turbine at low pressure through the exhaust pipe. If a certain mass of steam is considered as the thermodynamic system, then the energy equation becomes Q equal to delta Ek plus delta Ep plus delta U plus W. To analyze the expansion process in turbine, the moving system is to be followed as it travels through the turbine, taking into account the work and heat interaction all the way through. This method of analysis is similar to the Lagrange method of analysis in fluid mechanics. Instead of concentrating attention upon certain quantity of fluid, which constitutes a moving system in flow process, attention is focused on certain fixed region through which moving system flows. This is similar to the method of Euler in fluid mechanics. In this case, fluid continuously flows across the control surface, and this is a open system. When fluid flows through control volume, its thermodynamic properties may vary along the space coordinates as well as with time. So if the rates of flow of mass and energy through the control surface change with time, the mass and energy within the control volume also would change with time. For example, if about 5 kg per second mass flow is taking place at inlet, and let us assume if 4 kg per second of mass leaving the control volume at exit, then 1 kg of mass is stored continuously in the control volume per second. It is changing with time. So steady flow means rates of flow of mass and energy across the control surface are constant. So in case of steady flow, if there is 5 kg per second mass flow rate of fluid is at inlet, then there will be 5 kg per second of fluid flow at exit also. In most of the engineering devices, there is a constant rate of flow of mass and energy through the control surface, and the control volume in course of time attains a steady state. At the steady state of a system, any thermodynamic property will have fixed value at a particular location and will not alter with time. Thermodynamic properties may vary along space coordinates but do not vary with time. So steady state means that state is steady or invariant with time. So after that, let us derive expression for steady flow energy equation. So for that, let us consider a steady flow device in which there is a continuous one stream of fluid enters and one stream of fluid flows out of the control volume. There is no accumulation of mass or energy within the control volume, and the properties at any location within the control volume are steady with time. So section 1, and 2 indicate the entrance and exit of the control volume. Then the following terms or quantities are defined with reference to this figure, which are A1 and A2 are area which have unit of meter square at inlet and exit respectively. Capital V1 and capital V2 are velocity, which have a unit of meter per second. Then small w1, small w2 are mass flow rate, which have a unit of kg per second. Then Z1 and Z2 are elevation above the datum. Which has a unit of meter, and then we have small v1 and small v2. They are specific volumes which have a unit of meter cube per kg. Then small u1 and small u2 are specific internal energy which have a unit of joules per kg, and P1 and P2 are pressure absolute, that has a unit of Pascal. 1 Pascal is Newton per meter square. Then dq divided by d tau is the net rate of heat transfer across the control surface in joules per second. Then we have dwx divided by d tau. It's a net rate of work transfer across the control surface, excluding the flow work at inlet and exit, and has a unit of joules per second, and tau is the time in second. Tau is in second, and subscript 1 and 2 refer to inlet and exit of the control volume. Then if we write mass balance, then we do mass balance, then as per the conservation of mass, that is law of conservation of mass, if there is no accumulation of mass within the control volume, then the mass flow rate entry must equal the mass flow rate leaving. So this can be written as small w1 equal to small w2, or this can be written as a1 v1 divided by v1 equal to a2 v2 divided by v2. This is called as continuity equation. Then after energy mass balance, let us do energy balance. So in a flow process, let us do energy balance. In a flow process, work transfer may be of two types. The first one is external work, and the second one is flow work. External work may be a shear work, and also it may be electrical work. Shear work may be shaft work, or maybe it is stirring work. It's electrical work. And the flow work is caused by the flow of fluid with a mass flow rate of mass of dm1 at inlet and dm2 at exit. So here in this expression, in this control volume, we have only shaft work, that is wx, that is external work, whereas this flow work is caused by mass of dm1 at inlet and dm2 at exit. Then the corresponding work caused by this flow is minus P1 V1 dm1 and P2 V2 dm2, which are at inlet and exit of the control volume. Here the negative sign indicates work is done on the system, that is flow of mass at inlet is P1 V1 dm1 is negative because here work is done on the system. Then the total work done is work involved is given by crossing the control volume is given by, it is W equal to Wx. Wx is shaft work minus P1 V1 dm1 is the flow work at inlet that is done on the system, plus P2 V2 dm2, it is the flow work at the exit that is done by the system. Then if this equation is written in the rate form, so this can be written as dW divided by d tau is equal to dWx divided by d tau minus P1 V1 dm1 divided by d tau plus P2 V2 dm2 divided by d tau. So this can be written in the next step like this. It is dW divided by d tau equal to dWx divided by d tau minus P1 V1 W1, where W1 is mass flow rate that is given by dm1 divided by d tau, plus it is P2 V2, then it is W2, that is W2 is nothing but dm2 divided by d tau, that is mass flow rate at exit. Since there is no accumulation of energy by the conservation of energy principle, the total rate of flow of energy streams entering the control volume must be equal to the total energy streams leaving the control volume. So that can be written as W1 E1 plus dq divided by d tau is equal to W2 E2 plus dW divided by d tau. Here E1 and E2 are specific energies carried by the fluid at inlet and exit, and dq divided by d tau is the rate of heat transfer across the control surface that is transferred to the system, and dw divided by d tau is the total work transfer across the control surface that is done by the system. Then let us substitute for this dw divided by d tau from the previous expression. So this can be written as W1 E1 plus dq divided by d tau equal to W2 E2 plus in the place of this dw divided by d tau, let's write down this term. So that is dWx divided by d tau minus P1 V1 W1 plus P2 V2 W2. Then after rearrangement, this equation becomes W1 E1. Let us bring this minus P1 V1 W1 to left hand side. So this becomes plus P1 V1 W1 plus dq divided by d tau, that is equal to W2 E2 plus P2 V2 W2 plus dWx divided by d tau. So here, as I already told, E1 and E2 are a specific energy at inlet and exit, and that specific energy is given by E equal to Ek plus Ep plus U. Here Ek is kinetic energy, Ep is potential energy, U is specific internal energy. These are all energies per unit mass, and this summation is the total specific energy carried by the fluid, and then that is equal to Ek is kinetic energy, that is V square by 2 plus Ep is Gz plus U, specific energy, and let us substitute this V square by 2 plus Gz plus U to the previous equation. So that can be written as W1 into V1 square by 2. In the place of E1 I am writing this one, plus Gz1 plus U1 plus I'll write down this term, that is P1 V1 W1. So it is P1 V1 W1 plus dq divided by d tau, that is equal to W2. This right hand term is W2. It is W2. In the place of this E2, summation of all the three specific energies are written, then this becomes W2 into V2 square divided by 2 plus Gz2 plus U2 plus I'll write down this term, that is P2, then V2 W2 plus dWx divided by d tau. But we have the expression specific enthalpy H is given by U plus PV, but we have a small u is given by H minus PV. So let us substitute this one for U1 and U2. Then the previous equation becomes W1 into V1 square by 2 plus Gz1. In the place of U1, I write down this H1 minus P1 V1. So it is H1 minus P1 V1, and then this plus P1 V1 W1. So it is plus P1 V1 W1 plus dq divided by d tau, that is equal to W2 into V2 square by 2 plus GZ2 plus in the place of this U2 I'll write down H2 minus P2 V2, so it is plus H2 minus P2 V2, then this term it is P2 V2 W2, so plus P2 V2 W2 plus dWx divided by d tau. Then in the next step we can write down by cancelling P1 V1 W1, and so here in this expression this minus P1 V1 into W1, then this plus P1 V1 W1 they get cancelled, so that becomes 0. Here in the right hand side this P2 V2 W2 with this negative symbol, that becomes minus P2 V2 W2 plus P2 V2 W2, they get cancelled and become 0. Then the equation can be written in this way, that is V1 square by 2 plus GZ1 plus H1 into W1 plus dq divided by d tau, that is equal to V2 square by 2 plus GZ2 plus H2, that is into W2 plus dWx divided by d tau. Now mass flow rate at inlet, it is equal to mass flow rate at exit, that is equal to W, so that can be written as W1 equal to W2 equal to W, that is actually equal to dm divided by d tau. So let us divide this equation, let us give this number as equation 1. So let us divide this equation 1 by this dm divided by d tau, or simply W. Then the equation 1 becomes like this, it is V1 square by 2 plus GZ1 plus H1. This W1 divided by W is 1, because W1 is equal to W, that is equal to dm divided by d tau, that is equal to, that's not equal to, it is plus dq divided by, it is dm. So if this dq divided by d tau is divided by dm divided by d tau is in denominator of the denominator, that will go to numerator, so d tau get cancelled. Then the numerator of the denominator remains in the denominator, so this dm remained in the denominator in this term, that is dq divided by dm, that is equal to V2 square divided by 2 plus GZ2 plus H2. Then this W2 is equal to W, then W2 divided by W. Here we are dividing this whole equation by this W. So W2 divided by W is 1, as W2 is equal to W. Then plus dWx divided by dm. Here also it is same as dq divided by dm. Let us take this one as equation 2. Here equation 1 and 2 are called as steady flow energy equation. Or simply it is called as SFEE. The terms in equation 2 are the energy terms per unit mass, and whereas the terms in the equation 1 are per unit time. The equation 2 is suitable when there is a single stream of mass entering and single stream of mass leaving the control volume. But whereas the equation 1 is suitable when multiple mass flow rate taking place into and out of the control volume. So this is the derivation for steady flow energy equation.